This is Unit 7, Video 13. In this video we will talk about enthalpies of formation. It's going to be a short and sweet type of video and concept, very fun. So what we'll do is we'll list the formation of different compounds, of a compound, from the elements. And then we will be able to tell how much heat it takes to form those compounds. So for example, here the compound we want to list is C2H5OH. This is called ethanol. A very fun-loving compound. And you can list, notice it has carbon, hydrogen, and oxygen in it. And you can actually form it from the elements carbon, hydrogen, and oxygen, just like so. Now what you do is you write the compound so that you have a 1 mole right in front of it. And then you make sure you balance the rest of the elements so that way they match, so you have 1 mole. So you use fraction numbers. You'll see fraction numbers a lot in these. And then you list the delta H, the heat involved in this formation. Now you'll notice that the heat of formations are going to be negative. They're going to be, for the most part, exothermic. And we call them delta H. We'll put a little F down here and a little 0 up above, looks like a degree sign. This degree sign in chemistry has been designated to refer to standard conditions. And standard conditions means 1 atmosphere of pressure, so essentially just room atmospheric pressure, and then 25 degrees Celsius, roughly room temperature. A little warmer than room temperature, but this is defined as room temperature. And the F means that we are forming the compound from their elements. So you can actually have delta H. When you write delta H's, you can put any subscript you want to refer to maybe a reaction or something, just to designate what you're referring to. Alright, so we're going to show you how these can be used to determine the delta H of reactions. So again, here's the same equation. This shows the formation of 1 mole of ethanol from their elements along with the delta H. So this is the same equation you've just seen. Now the delta H of any element, the delta H of formation of any element under standard conditions is 0 kilojoules. This is an important thing to remember. So memorize. And this simply means if you want to form an element, it doesn't cost you any energy because it's already an element. You begin with elements. To form compounds, that's when you actually get yourself energies that are involved. So if you look up the delta H of nitrogen, it'll simply be 0 kilojoules per mole. Same thing with oxygen, same thing with carbon. So all of these will be 0, 0, 0. That's the idea. All these are zeros. Okay? Now, what's neat is we can use these heats of formation. By the way, these heats of formation, delta H of formations, have been tabulated and put in a table. As chemists have already determined essentially every compound that we know of, we try to get the heat of formation of that compound. And these enthalpies of formation can be used to calculate the enthalpies of reactions. And you'll see what we mean here in just a minute. So here is a table that lists the enthalpies of formation of a bunch of different compounds. So for example, here is our ethanol that we've just seen. Ethanol has a heat of formation of the negative 277.7 kilojoules. Notice we have a formula here that lists the states as well. And notice carbon dioxide, well-known substance, has a heat of formation of negative 393.5. And notice water here has a heat of formation of negative 285.8. And watch that, make sure water is liquid if you need it, because water gas will have a different heat of formation. So this is just a small sampling, but in the back of textbooks usually you have huge tables that show you the heat of formations of the different compounds. Alright, and how are we going to use these numbers? Very simply, we're going to use an equation and a simple formula, rather not an equation, a simple formula, to get the enthalpies of reaction. What this says is the heat of our reaction, how much heat a reaction releases under standard conditions, is equal to the, you got the this big letter, this is actually sigma, the Greek letter sigma, of the heats of formation of the products minus the heat of formation of the reactants. Now, remember that delta, think of delta T, remember we said delta T was T final minus T initial. Really, any delta in science is final minus initial. Well, in this case, our delta is the final minus initial of the products minus the reactants. Products is the final destination. Reactants is the original destination. And what the sigma refers to is that you add up all the products. Say if you have two products, you have to combine both of the delta H's. If you have three reactants, you have to combine all three of the delta H's. And the N means you have to multiply by the moles. So if you have 2 moles of product of one of the products and 3 moles of the other, you have to multiply the delta H by 2 and by 3. We'll do an example and it'll make more sense. So this fancy equation actually just simply means add up the products and subtract from the reactants, because delta means final minus initial, or products minus reactants. So let's go ahead and do an example, and that will do it for us. So here it says, using the standard enthalpies of formation listed in the table above, calculate the enthalpy change for the combustion of 1 mole of ethanol. So now, this is a reaction where we're burning ethanol and oxygen to produce CO2 and H2O. So we can actually get the delta H of this reaction by using the heats of formation, by simply doing products minus reactants. So the delta H of our reaction will simply be products minus reactants. It really comes down to that. Products minus reactants. Alright, now what we need is we need to determine or look up the heats of formation of these compounds. So let me write the heats of formation right below them. Now, if we look up ethanol, C2H5OH, looks like it's going to be a little problematic here. Okay, so here we have the ethanol is negative 277.7. So let's put that down. Negative 277.7 for ethanol. Looks like now oxygen is actually 0 because oxygen is an element. So this is an element. Remember, the delta H of formation of elements is 0. That makes it easy. Let's look up CO2 and H2O. It's going to be messy. We'll just look up CO2. Looks like CO2 is actually carbon dioxide, negative 393.5. So we'll do negative 393.5. And looks like water was negative 285.8. Negative 285.8. Okay. Looks like the markings are not cooperating. So now we're going to do products minus reactants. Now the way we'll do this is we have to multiply by the moles. So we have to consider that there are 2 moles of this and 3 moles of this. So we'll have to multiply 2 times the 393.5. Again, our delta H of reaction, this is what we just had up, is products minus reactants. So our products are 393.5 times 2. So we'll do 2 times 393.5 for the kilojoules. We have to add up. It's the sum of the products. Remember, it said the sum of the products. So I'm going to add up the second product. So 3 waters times negative 285.8. So 3 times negative 285.8. Whoops, I forgot the negative. Don't forget the negative. That should be a negative here as well. You have to keep track of the negatives. Alright, so you sum up the products and you subtract that from the sum of the reactants. Now, you only have 1 mole of ethanol, so it's just negative 277.7, and you get to add 0 for the water. 0 times 3. I'll go ahead and write 3 times 0 rather. I'll do 3 times 0, which won't really matter. Okay, now I'll also do this. Let me do this to help. I'm going to put huge brackets around the products and then huge brackets around the reactants, just to make sure that the math comes out correct. What I would recommend is kind of doing this step by step so you don't skip a few steps and then lose a negative or something. So let's go ahead and multiply the 2 by negative 393.5. That should give us negative 787. And we're going to add 3 times negative 285.8. That should give us negative plus negative 857.4. Okay, so now we've got these brackets. These are our products. We're going to subtract the reactants. Now, in this case, because we're subtracting a negative, remember when you subtract a negative, you're essentially adding. So we're really adding 277.7. Since this is 0, that doesn't really matter. Let's go ahead and combine these numbers here on the left side. So we got these two should give us negative 1,644.4. Hopefully that's what you've got. And then I get to add that to 277.7 and see what we get. So negative 1644.4 plus 277.7. And I should get negative 1366.7. Now in this case, because we have the decimal place in each case, we actually keep the decimal place. And this would be kilojoules. So what we've figured out is the delta H of a reaction from the heats of formation. And this would be the delta H that you would put at the end of this reaction. So again, this is a combustion reaction, should release a bunch of heat, and lo and behold, it releases 1366 kilojoules, which is in keeping with a nice combustion reaction like ethanol. So you can do this actually for any reaction you wish, as long as you have the heat of formations, as long as you have a table for the individual compounds. Now where this comes from is essentially Hess's law. Hess's law is first used, Hess's law that we saw last time, is used to calculate these heat of formations. And once you get the heat of formations, you have a table, and then you can propose any reaction and determine the heat involved in that reaction. Alright, so this wraps up the video for us, and we'll do example problems together.